Okay, so we're going to be using implicit differentiation here again. So a real quick reminder here, with this finding dy dx, this should follow right along with the sheet that you have. Think of this as your notes. So we're finding dy dx. Cosine of x is just negative sine of x. And then plus, and we have x squared times y, so we're going to need to do product rule. So I'll do the derivative of the first, 2x times the original second, y, plus the original first, x squared, times the derivative of the second, so the derivative of y, that's dy dx. I'm going to run out of room here, so I better move all this over. Okay, and then plus, and this 4 here is a constant multiple, so that just goes up right along for the ride. And then the derivative of y cubed, I have to do chain rule because it's y, but something is happening to it, it's cubed, so times 3y squared dy dx equals, and then on the other side I took the derivative with respect to x of 10, and I just get 0. All right, so now I have 1, 2, let's see, I have this 1, 2, 3, 4 terms, and this one right here has a dy dx. This one right here has a dy dx. I'm going to leave those on this side and move the other ones to the other side. So I have x squared dy dx plus 12y squared dy dx equals, and I have this horrible habit of being about to run out of room, equals, then it's going to be positive sine of x minus 2xy. All right, now I factor out a dy dx times x squared plus 12y squared equals sine of x minus 2xy. And finally, I divide all of this stuff over. So dy dx equals sine of x minus 2xy all over x squared plus 12y squared. Okay, so that's implicit differentiation. That's stuff you should already know how to do. That's a problem that could have been right on your test over implicit differentiation. All right, moving on. So suppose x and y are functions of t, then differentiate the following equation with respect to t. So first of all, I'm going to rewrite this real quick. This is x of t squared plus y of t squared equals 4. Now I'm taking the derivative of both sides with respect to t. So I see right here that x of t is being squared, that y of t, some function of t, is being squared. So I'm going to need chain rule for both of those. So the derivative of the first one is 2x of t. That's the derivative of the outside. 2x of t to the first. I plugged back in the x of t times dx dt. And then I have a plus sign, and then the second one I'm going to have to take the derivative of the outside, so I bring down the 2, plug in the old inside, y of t, and then times dy dt, and then on opposite side equals 0. All right, so that's the derivative with respect to t, and like we talked about on that worksheet, hopefully you've already went and checked your answers to that. Here we have 1, 2, 3, 4 separate variables here. 4 separate variables, and hopefully you know what all of these stand for. So it says in part B, if dx dt equals -2, find dy dt when x equals 1. So let's just start plugging some stuff in. So I've got 2, and then x. I'm given a value for x, so I'm going to plug that in, times 1. And then I'm given a dx dt times -2. So this is one term, plus 2, that's there, times y of t. We're not given a y of t yet, so I'm going to put y of t still here, times y of t times dy dt. That's what we're trying to find, so we don't want to plug in anything for that. And dy dt equals 0. We're trying to solve for dy dt, so it would be great if that was our only variable left, so we could get it alone and just have numbers left over. However, we have one more variable here that's causing us a problem, an issue. We have this y of t still in the problem. So what we need to do is figure out how can we get a value for y of t. If we know x is 1 and we have this original relationship, x squared plus y squared equals 4, we can use that to get a value for y. So I'm going to use that down here. I know x squared plus y squared equals 4, and x equals 1. So this implies that 1 squared plus y squared equals 4. So y equals square root of 3. So now I can use that to plug into my equation for y of t here. So I'm going to do a little simplifying now. 2 times 1 times negative 2 is negative 4 plus 2 times square root of 3 times dy dt equals 0. So I plugged in the value I got for y into the equation. Now all I have left is dy dt. That's what I wanted. Okay, so I add the 4 over and I divide, and I get dy dt equals 4 over 2 root 3, which is 2 over root 3. Oops, 2 over root 3. All right, going on. Okay, given that the volume of a cone is this equation, find dr dt when r equals 2, h equals 3. We're given a bunch of unknowns. So first of all, we're going to have to take the derivative of this whole thing with respect to time. So we got to realize that this equation is really v of t equals 1/3 pi times r of t squared times h of t. Okay, so on the left-hand side, when I take the derivative with respect to time, I just get dv dt equals, and then 1/3 and pi, or 1/3 pi altogether, that's just a constant multiple, so that goes along for the ride. So 1/3 pi. Don't need to do anything with that. Now this next part with this r of t times h of t, or r of t squared times h of t, I'm going to need to use product rule for. So I'm going to leave myself some space here to do product rule. I'll do the first one as it is. So r of t squared times the derivative of the second, that's dh dt, plus the second by itself, that's h of t, times the derivative of the first. And here I need to use chain rule. So times 2 r of t dr dt. So there's my derivative. Now all I have to do is just plug things in. We're trying to find dr dt. Let's see, we're given dv dt is 1/2. Is 1/3 pi. R is 2, so I got 2 squared. dh dt is 3/4 plus h is 3 times 2 times r is 2, and dr dt, well, that's what we're trying to find, so that stays in our equation, dr dt. Okay, now it's just some simplifying. 1/2 equals 1/3 pi times, well, this is 4 times 3/4, so that gives me 3, plus 3 times 2 is 6, times 2 is 12, 12 dr dt. All right, and now I'm going to not distribute. I'm instead going to multiply each side by the reciprocal here. Well, I'm going to multiply each side by 3 over pi, because that's going to get rid of this if I multiply this side by 3 over pi. So on this side, I've got 3 over 2 pi equals 3 plus 12 dr dt. Subtract the 3 and divide by 12 to get my final answer. So 3 over 2 pi minus 3 equals 12 dr dt. Divide both sides by 12. 3 over 24 pi minus 1/4 equals dr dt. Okay, so all we did was we plugged in for all of our variables except for the one that we wanted to solve for, and then we went ahead and solved the problem to get that one variable by itself. All right, let's go on again. Okay, so Sheila walks to Foster Park, throws a rock into the St. Mary's. Since the river is calm, ripples in the shape of concentric circles are formed on the water. Assign variables to the area and radius of one of these circles. Well, the area, that would be a good variable to call A, and the radius, let's go ahead and call that R. Okay, set up an equation relating these variables. Well, we're talking about circles here. Is there any equation we have that relates the area and the radius of a circle? Well, yeah, that's A equals I R squared. Okay, so once again, we can think of all of these things as functions of t. I might stop writing that right now, just because it saves us some time. But think about it that the area is increasing over time. The area of these circles as these ripples spread out over the water, and the radius of one of them is increasing as well. All right, let's go on. Car A is going west at 50 miles per hour, so here's car A, and car B is going north at 60 miles an hour. So car A is going like that way. Car B down here is going north. So car B is going that way at 60 miles an hour. Both are headed for, oh, I was wrong. Car A is going west. Don't know my north, west, east, south, all of those things. Okay, so car A is going that way, car B is going that way. Identify what the following variables represent and an appropriate label for each. So X right there, remember they're both headed for an intersection of the two roads. So X is the distance away from the intersection of car A. And Y is the same thing, the distance away from the intersection of car B. And S, well, S, if we look right here, that's the straight line segment that goes between the two cars. So that's the distance between the cars. And all of these things are distances here. And if we notice, our speeds were measured in miles per hour. So all of these distances, a good unit for them would be miles, miles, miles. Now, dx dt, that's the rate of change of x with respect to time. So how x is changing over time. How is this up here, this black arrow that we've got, I'm going over it right now. How's that black arrow, that distance changing over time? Well, that's the rate that car A is traveling. Or let's be a little more specific. Not the rate at which car A is traveling. I'm going to write it down here below. The rate at which the distance from car A to the intersection is changing. The rate at which the distance from car A to the intersection is changing. So that's going to be right there in dx dt. And now dy dt, we're going to have the exact same thing as above, only we're going to put car B. It's the rate at which the distance from car B to the intersection is changing. Okay, I wanted to say that rather than something a little vague about the rate at which they're traveling, because we've got to account for the fact that dx dt, the rate of change of x here, is actually going to be negative because x is shrinking. If you look up there and imagine car A traveling towards this intersection, x is shrinking, so it's getting more negative. Okay, so dx dt is the rate at which the distance from car A to the intersection is changing. Dy dt is the rate at which the distance from car B to the intersection is changing. And now ds dt, I'm going to rewrite this over here on the side. Ds dt is the rate at which the distance between the cars is changing. that's what all our variables stand for. Each of these variables, these rates at which they're changing, these would be in miles per hour. Miles per hour and miles per hour. Okay, set up an equation relating x, y, and s. Equation relating these three things. X, y, and s are all distances along the side of a right triangle. So an equation relating them, why that's Pythagorean theorem. So x squared plus y squared equals s squared. Okay, so now all of these are functions of time. X, y, and s are all changing over time. So we're going to differentiate implicitly. So this becomes 2x dx dt plus 2y dy dt equals 2s dx dt. And we have to plug in the values of our known variables. So the values of our known variables, I'm going to look back at my problem here from the beginning. I know car A is going west at 50 miles an hour. So x is shrinking at 50 miles per hour. So dx dt here is negative 50. Car B is going north at 60 miles an hour. So y is shrinking at 60 miles an hour. So dy dt is negative 60. Okay, do we know anything else? No, I don't think we know anything else. So we have 2x times negative 50 plus 2y times negative 60 equals 2s ds dt. So, excuse me. If we thought about an appropriate solvable calculus question, if we want this question to be solvable, we got to be solving for one variable here. We have to be solving for one variable. So let's say we need to give some more variables. So let's say car A is 20 miles from the intersection. Think about what variable that just gave right there. Which of these variables did I give away? I gave in my problem x, y, s, or ds dt. That one right there is x. So if we know car A is 20 miles away from the intersection, we know x. So, and let's say car B is 30 miles away. Well, that's going to give us y. So there we have x and we have y. Now, if we have x and y, do I need to give s in my problem? Well, think back to what we know. We have this equation right here that relates x, y, and s. I can do x squared plus y squared equals s squared, plug in my values for x and my values for y, and that gets me s. So right here, this has given me x already. This has given me y already. Those together are going to give s. So that's left ds dt as the only variable. So that's the one that we would ask our calculus student if we were writing this question to solve for. So how fast is the distance between the cars changing? So once we give those variables, we're down to only having one unknown variable in our equation, that ds dt, which is the distance between, the rate of change of the distance between the two cars. So that would be a good calculus question for this setup. Okay, we're moving on here now. Moving on, last one, I think. So a person 6 feet tall walks away from a streetlight 18 feet above the ground at a rate of 5 feet per second. Now, a very important thing for us to do in all of these situations is to draw a picture. So here's going to be my streetlight. There's a little light at the top. This is 18 feet tall. And the person is walking away from the streetlight. So I got to draw a little person in here. The person is right there. Got to have their feet on the ground. This person is 6 feet tall. So this person is 6 feet tall. So as the person's distance from the street light increases, so does the length of her shadow. Now, what things do we not know in this situation? Well, we don't know the distance from the person to the street light. Maybe I should put a little head and arms on my person so you know that we've got a human being here. Okay, we don't know the distance from the person to the street light. Let's call that x. And we're talking about this person's shadow here. So there's where their shadow would be if the street light was going. We don't know that distance. Let's call that y. Draw a picture showing all known and unknown variables. Okay, so we're going to set up an equation relating the distance from the street light and the length of the shadow. Distance from the street light and the length of the shadow. So if we think about this right here, what we've got, I'm going to draw in another line here. This is the light going down that makes the shadow. We've got two triangles here. We've got this big triangle, and then we've got the triangle that's contained in it. Here, I'll draw this one on top of it. We've got the big triangle, and then this triangle that's contained in it. Now, what we know about these two are that they are similar triangles. Similar triangles right here. So I've got two similar triangles. Now, similar triangles have proportional sides. So in this big one, that's 18. In the small one, it's 6. And the big one along the bottom, we have x plus y. And in the small one along the bottom, we have y. So that's how we can find an equation relating these things. So let me get a little space here. Oh, looks like those aren't going to split. So my equation here is 18 divided by x plus y equals 6 over y. So I match up the corresponding sides, the 18 and the 6. Corresponding sides go on the top, the x plus y and the y. Corresponding sides go on the bottom. Now, I'm going to want to differentiate implicitly. So before I do that, I'm going to multiply. I'm going to cross multiply here to get 18y equals 6x plus 6y. Because that's going to make it easier. Now I don't have to use the quotient. So when I take the derivative here, I get 18 dy dt equals 6 dx dt plus 6 dy dt. And now I want to plug in the values that I know. I'm going to plug in the values that I know. I know that the person is 6 feet tall. Where does that go in here? Well, in this equation, it doesn't go in anywhere. Okay, so the height of the person, that would be right here. That doesn't need to go in anywhere. Do we know either dx dt or dy dt? Those are two variables in the problem that we don't have yet. But looking up in our words, we have that the person is walking away at a rate of 5 feet per second. So that means dx dt is 5. So we can plug that 5 in for dx dt. Now, since we're down to one variable, our question should be fairly easy to write. We could write something like how quickly is the length of the shadow increasing. Okay, this should give you a good basis for understanding the problems that we're doing. I want you to go on and try to do some of the problems on the back page. Check back here on my website tomorrow for a video of an example going over a couple of those problems. So see if you can do a few of them, then check back tomorrow to see if you're doing them correctly.